NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman Lecture Series, our first of 2021. Tonight we'll be delving into the unique engineering of spacecraft origami. Now, origami as an art form dates back thousands of years, but in terms of engineering, it really only started to blow up in the past 20 to 25 years. Origami gives our technologists a useful and fruitful way of solving problems. Now, speaking of problems, if we run into any technical difficulties or small failures, we ask for your patience and stick with us tonight as we get them sorted out. As always, we like to remind you that this is your space program, and we want you to be involved in the conversation. Please ask questions in the chat, and we will try to implement as many as we possibly can throughout our discussion this evening. If you do not see the chat, go ahead and refresh your page, and it should be right there. And joining us as co-host, fielding your questions this evening, is our public outreach specialist, Talia Khan. Hi, Talia.
Hi, Brian. Thank you for that introduction. And thank you to all our viewers at home for joining us this evening. As a reminder, we will be taking questions through the chat and Facebook. So please feel free to pop your questions in there and we will get to them throughout the evening. Now I think it's time we get this show started. Brian, back to you.
All right, back to me. And yeah, let's get this started. We've got two speakers this evening. And our first one is a technologist in the Advanced Deployable Structures Group at NASA JPL. His research interests include large, unfoldable, origami-inspired structures, ultra-thin composite materials, and thin membrane structures. He received his PhD from the California Institute of Technology in 2016. Before we started, he reminded us how much he truly loves his job. Please welcome Manan Arya. How you doing, Manan?
I'm doing well. How you doing, Brian?
I'm doing great tonight because we get to talk about this wonderful little, it's not little at all, this wonderful technology. What was your inspiration? How did you get started with this in particular?
Well, so when I started in graduate school, I was really fascinated by these spacecraft called solar sails. And these are these spacecraft that unfold out these incredibly thin, incredibly large gossamer membranes, sails that catch sunlight, that generate thrust through the pressure of sunlight bouncing off these very lightweight sails. And I was really interested in thinking about how we may enable smaller and more lighter weight spacecraft to unfold out these large sails. And the problem ends up being, how do you unfold out these large, almost tennis court sized sails and fit them into tiny satellites? And that got me into thinking about, well, how have other people approached this challenge? And it turns out that there's been a lot of thought and a lot of exploration of how to take these large sheets of material and fold them down, thinking about the mechanics and the rules and the physics behind paper folding or origami.
So this field, as we talked about, has already blown up kind of in the past 20, 25 years. It's a bit of an esoteric job description because you're thinking, talk about how this has really grown up in the past couple decades.
Yeah, so origami, as you said, existed as an art form for thousands of years. And it's only in the past, century, half century, that mathematicians and physicists and engineers have started thinking about origami in a way of thinking about the rules that govern the folding of paper, in terms of thinking about how do we design new forms, how do we design new forms of origami, and also thinking about what are the physics, what are the mechanics behind paper folding, and how can we apply those mechanics to something other than paper. So people have come at this field of origami science or origami mathematics or origami engineering in a number of different ways. We've had sort of computational geometers think about origami as a way of creating new forms and new geometries. We've had my favorite example is actually has a JPL connection. His name is Robert Lang, and he's a giant in the field of origami engineering. But he used to be a laser physicist back in the day, and he came at it from the standpoint of being able to describe sort of the mathematics that governs origami forms, and he has designed new ways, new algorithms for designing origami structures. And this field has really started to explode in the past 20 to 25 years when we've realized that origami is amenable to mathematical description and to thinking about really the mechanics and the physics behind paper folding.
Very cool. We've got an image of you standing in. It's a cool image because you're standing. It's almost like your album cover. You're standing there in front of your work. What is this you're standing in front of? And then we'll look at the next thing that you've got there and some of the work that you've been up to.
Definitely. So that is a prototype antenna that we worked on, and I must say that it's not just me who works on these things. There's a whole team of people involved in building these structures, and that antenna in particular was designed alongside Richard Hodges, Jonathan Souter at JPL, and Sergio Pellegrino at Caltech. And it's an antenna that's about 6 feet by 6 feet, and yet it falls into a compact package the size of about, I don't know, a toaster oven. And the idea is to take this large antenna and package it into these very small satellites that are now becoming very useful called CubeSats. And these CubeSats are sort of briefcase toaster oven sized satellites that you can send up for not a lot of money, but that can do incredible science, especially if you unfold out these large structures from these CubeSats, like that antenna that I'm showing. Yeah.
Yeah, let's see an example of that. We've got actually something folding in on itself here.
Yeah, so this illustrates how that antenna would fold up. And this is a structure that was a prototype actually that we made for that antenna. And this is made out of ultra thin, ultra lightweight carbon fiber materials. And as you see, it goes from being about a meter across by a meter across to that very compact package right there.
Very cool. We'll go to our next image, and I want to ask you, as we're looking at something like this, why is this important?
So it comes down to the fact that when we launch things into space, we are always restricted by how much volume, how much space we have available in our rocket fairing. Rocket fairings are only so much, only so big. And if we want a structure in space to be bigger than what is allowed in the rocket fairing, then we need to somehow find a way to fold that structure up inside the rocket fairing, launch it, and then unfold it when it gets to space. And this is important when you're trying to have large structures in space that are doing things like collecting solar power, where obviously the larger structure you have, the more power you collect and the more capable your spacecraft can be. Or as in the previous example, something like an antenna aperture, where the larger the antenna aperture you have, the more gain you have, the better you can communicate back to Earth, or the more resolution you have for doing things like remote sensing. So it's trying to break what is typically called the tyranny of the fairing. You have only so much volume available. How do we make structures that are bigger than that volume available to spacecraft in space?
Well, let's actually show you trying to defeat the tyranny of the fairing with a video of this really opening and closing.
Yeah, so this was a prototype structure that we made. So that's myself and my intern Chris taking this carbon fiber structure and showing how you can package up these sorts of structures in a compact way, but also that the structure, when unfolded, kind of sustains itself. It has stiffness on its own, and it's able to maintain its own shape under Earth gravity loading, like right there.
Very cool.
And this was a prototype structure.
Sorry, go ahead. No, no,
Oh, this was
please.
a prototype structure we developed to investigate how we may package up large solar arrays and structures like that.
Oh, wonderful. As we go to our kind of the last video, last little bit of us talking to you, and we'll come back to you later. We want to talk about what's next. And there's a cool little video that we've got too that gives a little example of it. But really, from your opinion, what's next?
Yeah, I think people have really started exploring the edges of what's possible with sort of traditional single sheet of paper origami. There's still a lot more to be studied about that problem, but people are now approaching this from the perspective of how can we extend origami? How can we make new forms that are not possible with just a single sheet of material? So the structure that you saw me unfolding in the previous video has this kind of wavy character to it that is not possible with a single sheet of paper. In the video that's coming up, we're exploring the kinds of forms that are possible by assembling structures in a modular fashion using components that are individually based in origami. So
So
if you could have that
number five,
next video,
yeah, there we
yeah.
go.
So this was a proof of concept foldable robot that this brilliant intern Alexandra Harasti from Caltech developed for us this past summer, and it's a excuse the motorcycles.
We're live, yeah.
This was a study into how can we take these sorts of robotic bodies, package them up in a compact way, such that when we go and want to do exploration with these robots, we can pack many of these robots into a mothership, and then when they get to their destination, we can deploy many robots for multi-agent exploration of a surface using these stiff but still foldable robots that you can package many of in a compact volume.
Very cool. Is there anything that our audience can do at home with this?
Oh, definitely. That's the wonderful thing about origami is that it is really accessible to almost everybody who has a flat surface and a sheet of paper. I think we have a link to some folding instructions for folding up these kinds of wrapping origami structures. So this is a fold pattern that was developed for an effort called that was trying to mature star shade technology, and you can go to the website and there's instructions and a pattern that you can print at home and then fold to see how we're packaging up these very large structures into compact volumes by means of wrapping in an origami fashion. And I actually have a tiny version of that over here. This is not exactly the same fold pattern, but it's akin to the fold pattern that instruction set provides you.
So everybody at home could start this tonight. They could go on there, they could print it off, and they could start folding, and they would have that, what you're seeing on that screen right now.
Exactly.
Such wonderful, and I know people are asking lots of questions today. So, Talia, what's going on with the chat today?
Yeah, so we have lots of amazing questions in the chat. One in particular stands out. So Jared on YouTube is asking, repeatedly folding paper can compromise the crease edges. How do you overcome this when you're repeatedly testing solar sail deployment?
That's an excellent question. So typically, we tend to use paper for initial prototypes and initial studies of the geometry and the forms of these structures. But when we switch to using these kinds of structures for space engineering applications, we switch materials to something that's a bit more robust than paper. So in the case of solar sails, we tend to use space grade thin plastic sheets. The jargon is polymer membranes, and these polymers are tend to be space grade and a lot more robust than paper. So in the case of solar sails, we think of things polymers called polyimides, which are a lot more tough than paper. and they can be folded, creased repeatedly many times, and then unfolded. That still is a challenge, though. The idea that after repeated creasings, even materials as tough as polyimides can degrade and crack. So that always presents a challenge for us.
Wonderful. And earlier we talked a little bit about how some of these structures get deployed into space. So Carol on Facebook wants to know, does the lack of gravity in space impact the designs? And do you face any challenges with the origami structure and deployment?
Oh yes, that is one of the sort of the most ubiquitous challenges when it comes to designing these kinds of structures, is that we have to test them on the ground. We have to make sure that they unfold correctly while they're still on the ground to make sure that they will unfold in space. But testing these kinds of structures on the ground has the side effect of there being Earth gravity on the ground. And we can't exactly flip a switch and turn that off. So how do we meaningfully test the unfolding of these structures in an Earth gravity environment when their operational environment has no gravity? So we have to engineer ways of doing what we call gravity offload or gravity compensation, where these structures are either strung up with strings and counterweights, or they're resting on air bearings on very flat tables, or they are resting on sprung supports to counteract the weight of the structure. And this idea and this challenge of gravity offload has been solved many different ways, and each structure sort of brings with it its unique challenges in terms of gravity offload. And then what that means is we have to not only design the structure to function in the environment of space, but also in a gravity offloaded Earth environment. And that brings with it its own challenges. It's a really fun, challenging set of issues or set of challenges that we have to deal with.
Very cool. We'll bring Manan back in a little bit for more questions, but our next speaker is a creative technologist in the studio at NASA's Jet Propulsion Laboratory. She holds a BFA in illustration, entertainment, art, designing vehicles, props, and environments for feature film animation from Art Center College of Design. She uses design thinking methods and techniques to imagine the future of technology in space. She earned her MS with the MIT Media Lab, focusing on space technology development, and works on creative projects and tech demos for various space missions. She is one of those people reminding us that we can always dream bigger. Please welcome Lizbeth De La Tour. Hi, Liz.
Hello. Hi there. Thanks, Ryan, for having me.
Of course. Let's talk about some of your inspirations, some of what you called informal robotics.
Yeah, absolutely. So, similar to London, this happened for me during my graduate studies at MIT. I was fortunate enough to be able to take a course at Harvard's Graduate School of Design, which is just down the road from MIT. And it was a course taught by Chuck Hoberman, who's a wonderful engineering designer. It was really about rapid prototyping of robotics, taking paper, very raw materials, and quickly creating prototypes that move and that can walk, swim, fly, those sorts of things. And so I was really inspired in that way. It was a lot of origami techniques within this course. And I was really inspired about taking the complex movements of animals, the biomechanics that animals use to walk and crawl, and translating those through origami. So you can imagine a flat packed robot that can then pop up and walk around, maybe inspired by a mollusk or by a butterfly, and those sorts of things.
Well, speaking of butterfly, let's actually go to our next image because you're a creative designer, and something you've talked to me about is simplification.
Yes, absolutely. So, as a designer, we were taught to simplify everything, and that includes, for me, going into paper and simplifying those complex movements of animals. This is just a really rough example of how you might go from something flat in paper to something that moves. And always, when considering these animal inspired robots, it's always important to remember too that animals come with stories attached to them, and we sometimes attach stories to the robots that we create as well, and a lot of cultural significance for certain animals. For me, my family's Mexican American, and so butterflies have special meanings for us. But translating that and creating that movement here, actually, if you go to the next slide, we can kind of see it, how that might move. And so all of those, what Manan was talking about, the flat folding, those flat folds can then become engineered linkages that can, you attach a motor to it or an actuator, and they will move however you would like them to move. And it's great because it's very predictable. Mathematically, you can predict exactly how something will move. And I think that was really valuable.
Well, something you talked to me, you mentioned a mollusk before. And when I look at a mollusk, that's not immediately the first thing I think of for, make a spacecraft out of that. If we go to our next image, talk to me a little bit about this with these folds.
Yeah, so this was a project done at MIT with Jiani Zhang and Elena Kodama. And really, it's actually exactly the same paper fold that Manan was sharing earlier with the four-wheeled robot that can flat fold. This is the Mirafold. And we used this, actually, we studied mollusks for quite a while. So the movements of snails, snails that you might think are actually very simple, but they're actually very high-tech. They move in very special ways, and to recreate those movements actually was quite a feat. But with the Mirafold, we were able to create the motion of the mollusk and how it pulls itself along the ground using a lot of traction and actually padded feet. And so we created this, this very fast paper robot that can do the same thing or a similar thing. And yeah, and actually, I think if you go to the next slide, I can also share what the assembly looks like as well. Yeah, and so actually, so what we did, it's a very fast technique where we pre-etched the mountain and valley folds. So all of those folds are actually, it's a combination of hand folding and also mechanics. So we attached an actuator to it, we 3D printed the spine and kind of put it all together. So it was actually very, both art and science combined into one, which is really very nice.
Very cool. As I asked Manan, and I'll ask you, why is this specific style important?
Yeah, and so actually, so we go to many different planets, and we explore many different environments, and I find that nature has solved a lot of the problems that we're facing already. And so being able to translate those complex movements through origami is actually very useful for exploration of terrains that we might not have thought of going to before.
Very cool. So what's next in biomimicry?
Yeah, so a lot of researchers looking into embedded electronics. How do we, specifically with folding of polymers, just looking at how are you able to embed electronics directly into the folds, because sometimes you need a shell or some kind of body to house the electronics. And so right now it is definitely a lot of looking at how can we create maybe just a flat sheet that can walk around and those sorts of things. So yeah, I think that's
very
next.
Cool. That's what's next. And speaking of what's next, let's bring Talia back in, who's been watching the chat, and see if there are any more questions.
Yeah, so we have a lot of great questions. Andres Jose on LinkedIn wants to know, how much more vulnerable do these electronic components become when you begin folding them in?
Oh.
That's a great question. Actually, so it really depends on the robot. So in this case, the robot on the screen here has a shell similar to a mollusk. And actually, that was very useful. So sometimes there is a housing or encasing that will protect them very well. And so far, once you do start embedding a circuitry right into the folds, there is kind of some tension when you start folding, and that the copper of the circuitry starts to kind of fold along with it. There's some tension there.
Great. So Anne on LinkedIn wants to know, does the requirement for folding these spacecrafts increase the likelihood that they'll fail in space?
I think I can answer that one. So, I mean, ideally, we will have designed it very well on the ground before it goes into space. We will have already kind of accounted for all of any failures that might happen in space. So I think very well prepared.
Very cool. We're going to bring Manan back in now. This topic, and both of you, your experiences are a great reminder of how important STEAM is, not just STEM, but having a broad, wide ranging education. What are some of the unexpected influences, things that you didn't think would influence you, but turned out to be hugely important for this type of work?
Yeah, so I can go first, if
Great.
that's okay.
Yeah.
Yeah, one of the things that has served as a sort of an unusual point of inspiration for me in the past couple of years actually has been the species of flower called the datura that is actually native to Southern California where we are, uh, and it kind of just grows wild here. But the thing that struck me really was the way in which the surface of the flower wraps up. As you can see, the bloomed the bloom has that amazing white surface fully unfolded. But when it's coming out of its bud, it is wrapped up in that very intricate sort of spiral format. And while it's unwrapping, while it's blooming, in that third image that you see, it kind of maintains its stiffness. It kind of has a stable shape to it because of this non-planar, out of plane sort of curvy behavior, the curvy form that it has, and that was partially an inspiration for designing that carbon fiber wrapped solar array prototype that we saw a video of, where when it was unfolded, it also had that sort of unfolded, curvy, sort of crenulated character that gave it some stiffness and stability. So, something as simple as a blooming flower can be really uh, can be inspiration for these kinds of structures.
Very cool. And Liz?
Yeah, absolutely. And I'll actually go back to the mollusk and talk a little bit more about mollusks. That was a really unexpected inspiration for me in graduate school. And I'll say that because, we walk by mollusks and snails every single day, on a sidewalk. And we just imagine that they're very simple creatures, but they're really complex, and it's actually, it has sensory feedback, right? Its little eyes there, and a mechanical motion that happens because of that sensory feedback. And so just recognizing for me that something very simple is actually, it was very hard to do. It was actually a very big inspiration for me.
Wonderful. We're going to open it back up for questions for both of you now. So, Talia, how's it going out there?
Yes, so we still have a lot of great questions coming in. Tom on LinkedIn though wants to know how much more cost effective are origami designs? Why are we doing origami designs instead of just sending up the entire spacecraft?
It's not so much a function of cost effectiveness versus just being able to fit a larger solar array or a larger antenna or a larger solar sail in a spacecraft platform which could not previously have fit that size of a structure. So it's more about enhancing capability and creating opportunities for these spacecraft to have capabilities that they could not previously have had, given the volume constraints that they have to deal with.
Great. So Abby on Twitter wants to know what are some of the more ambitious projects using folding techniques and origami that have been suggested?
So one thing I'm going to point to is the James Webb Space Telescope, which is due to launch sometime this year. And this is an incredibly beautiful space telescope that's going to unfold not only its primary mirror, which has two folds within it that helps the mirror be larger than the size of the fairing the mirror goes in, but it also unfolds out this tennis court sized sun shield that protects the mirror from the heat of the sun, and that's a remarkable project that is currently underway. That I think uses these kinds of folding techniques in an amazing way.
Wonderful. So, speaking of unfolding the Webb Space Telescope in space, Nate from LinkedIn asks, what kind of systems are used to unfold these designs?
It really depends on the application. Liz, if you can take a stab at, kind of the robotic implications of this afterwards. But in the case of, deploying these large structures, the motive force is sometimes a motor that is reeling in cables somewhere, or it's perhaps energy that is stored within the folded structure itself, where there is strain energy that is elastically stored within the structure that helps the structure unfold when it gets there. And oftentimes there is a secondary deployable structure, like a deployable mast or a deployable boom that unfolds out these large structures. But I know in robotics, for instance, different motive forces are used.
Yeah, absolutely. And in robotics, I like to imagine it as sometimes like opening a pop-up book in some way, and your hand is the motor, and you pull, and a motion happens. At least in my brain, that's always how it has worked. So when you think of a limb moving or an appendage moving, there's always that motor that is making that happen, and the actuator. It can be many different things. Some people use pneumatic actuation, or standard just regular old actuation with a motor. And yeah, and so that's usually it's kind of housed and encased somewhere within the body of the robot.
Great. So when we're doing origami at home, we're usually like making a butterfly or making a crane, and those are usually really, really delicate objects, right? So Krishnam on YouTube asks a really great question: how do these really delicate designs withstand a rocket launch?
Yeah, that is another one of those sort of quintessential challenges of designing these kinds of structures, and the answer ends up being, um, uh, using engineering principles and engineering design methods and techniques to make sure that the materials you use and the way you engineer them are able to withstand those launch forces. So typically, one does not use delicate things like paper. We use things like carbon fiber composite materials, or metals, or glass fiber composite materials to engineer these kinds of structures. And then, obviously, before they get even close to a rocket, there is tons and tons of analysis and work that goes and testing that goes into making sure that when these structures are within the rocket being subject to that incredible amount of vibration and acoustic noise, that these structures will survive. So there's an incredible amount of analysis and engineering and testing that that goes into the design of these structures. But from a fundamental standpoint, it's about using the correct materials in the correct ways to make sure they can withstand these forces.
Great. So you talked a little bit about, having to make sure that these materials withstand forces, but apart from that, Kier on LinkedIn wants to know what are some other current limitations that exist for designing foldable spacecrafts?
That's a really good question. Liz, do you want to take that?
Yeah, I can talk a little bit. So, of course, there's always the embedding of the electronics within the folds. That's something that has been a really big challenge for a while. And yeah, also even materials are always a challenge, right? Lots of testing goes into them, but really it depends on a lot of the environment that you'll be going to, and like for example, if you go to Venus, you need to coat it in Teflon because everything it's very acidic in those clouds. So I'm just thinking along those lines of there's both kind of the stability of launching, and then also once you get there, what happens to it. So yeah, a lot of different
Yeah.
problems in many different ways.
And from a
Great. And
large
that brings
structures,
Oh, sorry, go ahead.
sorry, I was just saying from a large structure standpoint, it's the challenges that face this community have to do with how do we make things bigger, because in many cases bigger is better. Bigger solar arrays are better and bigger apertures are better. How do we pack them into our spacecraft and into our fairings even more tightly? And how do we keep mass low? Because obviously, every pound launched is cost. That costs a certain amount of money. So you end up with these structures that are very large and very thin, and that ends up creating design and engineering challenges in its own right when you're having to deal with these. In the case of, say, solar sails, you're dealing with membranes that are so incredibly thin that it becomes a challenge to to package them and to test them. We're talking about membranes that are as thin as a few microns, which is about 1/100th the width of a human hair. So these are incredibly gossamer structures that we need to think about engineering and designing.
Very cool. We've
Yeah,
got time for
I mean-
one more question. Yeah.
All right. So, for both of you, Tim on YouTube wants to know, what's a lesson that you learned in school that still makes an impact in your work as creative technologists and just creatives?
Oh, I can take that one really fast. Yeah, and so I think that sometimes there are some mechanical movements that just a robot just won't walk, no matter how much you want it to, and no matter how much it looks like that fold will walk. And so I think a big lesson for me was learning how to move on from a design or how to improve it, or know when to move on to the next step. I think that was a big thing for me.
I really have to go back to my first class in civil engineering that I took, and my professor told me 3 rules that have always stuck with me, that are the most important for structural engineers like myself. The first one is F equals ma. The second one is you can't push on a rope, and the third one is to find the answer you must know the answer. Yeah.
Those are all great tips to walk away with. That's all the time we have for questions. But before we go, I did want to get just from both of you one final thought. What is, besides those wonderful tips you both just gave us, what is the one thing you'd like your audience to walk away with today? Let's start with Liz.
Yeah, so I think the biggest takeaway for me would be art and science are more similar than you might think they are. You might find inspiration for engineering in the DIY section of a bookstore. And yeah, you can start. What's great about origami is you can start working on it today at home with a piece of paper and just start folding. And yeah.
Very cool. And Manan.
Yeah, kind of echoing what Liz said. One doesn't typically think about origami when one thinks about engineering or science or math. There's all these ideas in people's heads about science, engineering, and math as this one thing and one thing alone. But I think it's been fun for me to realize over the course of my work that there are many entryways. There are many different ways you can approach science, engineering, and mathematics. And origami is one of those unexpected but wonderful ways where we find that something as tactile and as wonderful as origami has applications in engineering, and that's just a wonderful thing to realize.
Very cool. That is all the time we have for tonight. Please join us next month. We'll be discussing planetary protection with Dr. Mujige Cooper. I'd like to thank our speakers tonight, Liz De La Torre and Manan Arya, for their expertise, their kindness, and their joy. A reminder also that you can't push on a rope. Thank you to Talia and everyone behind the scenes that make these talks possible. And a big thank you to all of you who join us every single month. Please stay safe, stay kind, and we'll see you in February.